Yay!
Yay! Okay, now let's talk about the energy in simple harmonic motion, in spring motion. So the classic example is, suppose I have the block at the equilibrium position, the relaxed spring position at 0, and I'm going to pull it out to x, right? I got to put a force into that. I got to put some work into doing that using energy terms. So if I pull it a distance x, the question that we want to know is, what work have I done? Because the change in the potential energy of the system, the potential energy I've stored in the spring by putting the work in, is just going to be the negative of the work done, right? Because I've put energy into the system, so whatever work I've done, if that's negative work, then that's stored in the system, so that's positive potential energy. It's one way to look at it. The signs are always a little confusing. So anyway, let's see what work is done. So the work done is just going to be, I got my minus, I'm pulling this thing from 0 out to some final position, x, maybe we'll call it x final, just to keep all the x's straight. And then this is just going to be the spring force. It should be vector, right, dotted with the displacement, but I'm just moving it to the right, and the force I'm applying is to the right, so I can kind of forget about the dot product and the vectors that we did back in the energy unit. And so this is just going to be dx, right? It should just look like that. All right, so I know what the spring force is. It's headed back to the left. So this is going to be a positive 0 to xf. This is going to be a positive kx dx, right? Those negative signs are going to cancel. So that's going to be a pretty easy integral. The integral of x dx. It's just x squared over 2. So this is just going to be 1/2. So this means that the potential energy stored in the spring is going to be 1/2 kx squared. X final, if you want. Well, let's just call that x. So here's our spring energy. So when I pull a spring a distance x, I'm storing an amount of energy, 1/2 kx squared, in it. Okay. But what's cool is that now, if that's the energy stored in the spring, that should be good for any x, right? And then we already know what the functional dependence is of x on time. We know how this thing moves in time. So let's put in, at any time, x is just going to be a cosine omega t, is what we had before. Okay, so I'll put this over here. So our potential energy at some time, as this thing is oscillating, let's see, that's just going to be 1/2 k, and then that's just going to be x squared, right? So it's going to be a squared cosine squared omega t. All right, very cool. If that's the potential energy, I can also write down the kinetic energy. The kinetic energy for the spring system is 1/2 mv squared. But what was v? V was just the derivative of x, right? V at some time t. If I take the derivative of the x thing, what do I get? I pull out the minus omega a sine omega t. Cool. And so that's the thing that I'm going to square. So our kinetic energy at some time, it looks like that's just going to be, 1/2 mv squared. And so that's just going to be an omega squared a squared sine squared omega t. All right, neat. Ooh, look what we can do with that, though. Look at those two terms. What was omega squared? Omega squared was just k over m, right? So if I put k over m there, I can also call this 1/2 k, because that's what's left over. The m's are going to cancel. This is going to be k a squared sine squared omega t. And look at the kinetic term and the potential term. Look at that. It's got the same factor out front. So that, what if I add them together? If I add them together, what does that make? That's the total energy of the system, just kinetic plus potential, right? So the total energy of the spring system is U plus K. So if I factor out the 1/2 Ka squared, I'm going to have then cosine squared plus sine squared, but that's just 1, right? That's a trig identity. So look at this. The total energy of a spring system just depends on the amplitude squared. And look at what happens. It's not dependent on time, right? This is constant. Doesn't change. The energy of the system doesn't change. That maybe should not come as a surprise, but it's cool that we can show that for a spring system. Even though this thing is speeding up, slowing down, the amount of kinetic and potential is changing in time according to sines and cosines. It's kind of cool that the total amount of energy never ever changes. If you add them up, you always get the same value. It's constant. That's a deep insight. As you go further in physics, you're going to find out lots of deep connections between energy and time. The fact that energy doesn't depend on time, meaning that it's conserved, is a deep principle that goes through all of physics, really. Okay, so we have the total energy of the system, and then we have the kinetic and potential at any time. So let's just put some numbers in there. Let's see how this works for a particular system. Let's see, what did I use? I said a 50 gram for a 50 gram object on a 35 Newton per meter spring. That's the stiffness of the spring. And the amplitude of the oscillation is 4 centimeters, 0.04 meters. All right, so let's figure out some of these quantities. Let's make sure everything makes sense. I can figure out the total energy of the thing. So the energy is just 1/2 Ka squared. No problem. You just plug the numbers in. That's boring. And what you get is 0.028 joules. So can I just call this, what is that, 28 millijoules? It's more fun to have things without decimal points. Okay, 28 millijoules. Cool. Now, let's see how these things change depending on where this object is in its motion. About the B part. What is V when x equals 1 centimeter? This is a little harder question to answer based on what we had done before. I can get V as a function of time, right? We know that. But V depending on x is a little bit tougher deal. Because what you would have to do is try to figure out what time the particle is at a certain x coordinate and then plug that in. And that's a harder calculation. But it turns out using energy methods, it's actually pretty easy. Because where does the velocity come in? It comes in the kinetic energy term. So I can do this. Here's sort of a shortcut. I can say that the kinetic energy at some time is just the total energy of the system minus the potential at some time. Right? So what is the kinetic energy? The kinetic energy is just going to be 1/2 mv squared at this time equals ES. What was that? That was 1/2 Ka squared minus, what was US? 1/2 Kx squared. Right? Because we know what the x is. We know this is a particular x. So it must be a particular t. I can sort of drop that from the v term. Okay, well look, all the halves go away. Cool. So v, I just divide by m. K over m. K over m is just omega squared. Right? So this is going to be omega squared And it's going to be the same term in front of the x squared, right? So it's just omega squared, a squared minus x squared. So this is sort of a neat result. It's sort of a shortcut, so you can get the v at any x if you know the initial amplitude. So that saves a lot of time. These energy methods can often save a lot of time. Okay, well, we know all that stuff. We could figure out the, because we know the mass and we know the k, we can get the omega. And then you plug in the a minus x, and what you get out of that is that the v, if you want to try this out, is 1.02 meters per second. 1.02 meters per second. There you go. So that's how fast it's traveling when it is at that position. Okay, let's check something else. Let's make sure at some arbitrary point, let's pick, what did I pick? 3 centimeters, when the object is at 3 centimeters. Let's see if energy is conserved. So we're going to figure out C. Let's figure out the kinetic at 3 centimeters. So what is the kinetic at 3 centimeters? Well, we've already got that, right? The kinetic is just going to be 1/2 k a squared minus x squared. And what have I got? I got 12 millijoules if you plug in your numbers. And then let's do the, what is the potential at the same point? Let's figure out what the potential is. And the potential at that point is going to be 1/2 kx squared. That's going to be even easier. And when you plug in those numbers, what you get is 16 millijoules. And why that works out so nice is the total energy is kinetic plus potential. So if you add these things together, you sure enough get 28 millijoules, which is what we calculated back in the A part. So sure enough, just looking at some arbitrary point in the oscillation, it turns out energy is indeed conserved. Calculate the potential and the kinetic, and sure enough, it equals the same amount of energy at any point during the oscillation. So these energy methods can give you some real good insight into the physics of the system.